Electrostatic induction. It is possible to obtain charges without any contact with another charge. They are known as induced charges, and the phenomenon of producing induced charges is known as electrostatic induction. The following animation explains the electrostatic induction. Consider an uncharged metallic sphere on an insulating stand. Now, a negatively charged plastic rod is brought near the sphere. Therefore, deficiency of electrons create positive charge in the near end, whereas the accumulation of electrons on the farther end produces a negatively charge on it. Now, the negative charges on the sphere are grounded, that is, it is earth. The positive charges at the near end remains held due to the attractive force. Now, the sphere is removed from the ground and the positive charge continues to be held at the near end. Now, the plastic rod is removed. Finally, the positive charge spreads uniformly over the sphere. Principle of a capacitor. The following animation explains the working principle of a capacitor. Consider an insulated conductor which is named as plate A with a positive charge Q and having a potential V. The capacitance of the plate A is given by C is equal to Q by P. When another insulated metal plate B is brought near the plate A, the negative charges are induced on the side of the plate B near the plate A. An equal amount of positive charge is induced on the other side of the plate B. The negative charge in the plate B starts to decrease to the potential of A. The positive charge in B starts increases to the potential of A. But the negative charge on B is nearer to A than the positive charge on B. So, the net effect is the potential of A decreases. Thus, the capacitance of the plate A is increased. If the plate B is earth, the positive charges get neutralized. Then, the potential of A decreases further. Thus, the capacitance of A is considerably increased. Polarization of a dielectric. The following animation explains the polarization of a dielectric. A nonpolar molecule is a one in which the center of gravity of the positive charges coincides with the center of gravity of the negative charges. Example: oxygen, nitrogen and hydrogen. The nonpolar molecule does not have any permanent dipole moment. If a nonpolar dielectric is placed in an electric field, the center of charges gets displaced. They align themselves in the direction of the electric field. Therefore, nonpolar molecules are called induced dipoles because they acquire the induced dipole moment in the direction of the electric field. Polarization of polar molecules. This animation explains the polarization of polar molecules. A polar molecule is a one in which the center of gravity of positive charges is separated from the center of gravity of negative charges by a finite distance. Examples: N2O, H2O, HCl and NH3. Polar molecules have permanent dipoles. Without any electric field, the dipoles can orient themselves in random directions. When an electric field is applied, the dipole orient themselves in the direction of the electric field. Capacitors in series. The following animation explains the effective capacitance of a capacitor connected in series. Consider three capacitors of capacitance C1, C2 and C3 connected in series. One end of the capacitor plate is connected to the positive terminal of the battery. The negative terminal of the battery is connected to one end of the key. The other end of the key is connected to the plate C3. Let V be the potential difference developed across the cell. Each capacitor carries the same amount of charge Q. Let V1, V2 and V3 be the potential difference across the capacitors C1, C2 and C3. Thus, V is equal to V1 plus V2 plus V3. The potential difference across each capacitor is given as V1 is equal to Q by C1, V2 is equal to Q by C2 and V3 is equal to Q by C3. Rewriting the above equation, we get V is equal to Q of 1 by C1 plus 1 by C2 plus 1 by C3. If Cs be the effective capacitance of the series combination, it would acquire charge Q when the voltage of V is applied across it. Therefore, V is equal to Q by Cs. Q by Cs is equal to Q by C1 plus Q by C2 plus Q by C3. Cancelling out the common term Q, we get 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3. Hence, we can conclude that when a number of capacitors are connected in series, the reciprocal of the effective capacitance is equal to the sum of the reciprocal of the capacitance of the individual capacitors. Capacitors in parallel. The following animation explains the effective capacitance of a capacitor connected in parallel. Consider three capacitors of capacitance C1, C2 and C3 connected in parallel. The positive terminal of a battery is connected to the one of the plate of C and the negative terminal of a battery is connected to a key. The key in turn is connected to the other end of the plate C. A potential difference V is applied from the battery. The potential difference across each capacitor is the same. The charges on these three capacitors are Q1 is equal to C1V, Q2 is equal to C2V and Q3 is equal to C3V. The total charge in the system of capacitors is Q is equal to Q1 plus Q2 plus Q3. Therefore, Q is equal to C1V plus C2V plus C3V. But we know that Q is equal to Cp into V, where Cp is the effective capacitance of the system. Therefore, Cp into V is equal to V into C1 plus C2 plus C3. Cancelling out the common terms, Cp is equal to C1 plus C2 plus C3. Hence, the effective capacitance of the capacitors connected in parallel is the sum of the capacitance of the individual capacitors.